The Ground Transient Terminator, or GTT, is a device designed to be placed in series with the equipment grounding conductor, or EC, to mitigate the impact of ground transients on sensitive equipment. Its primary function is to safeguard equipment from potential damage by effectively diverting transient energy to ground. Ground transients are abrupt surges of high-energy electrical current that can manifest within the ground. These surges can arise from several sources, including lightning strikes, power line faults, and various switching operations within the electrical system. The effects of ground transients can be detrimental to equipment, encompassing damage to electronic components, data loss, extended equipment downtime, and potential safety hazards for personnel. The GTT operates as a passive device, meaning it does not necessitate any external power source for its functionality. It typically comprises a configuration of capacitors and inductors meticulously engineered to redirect transient energy safely to ground. The installation of a GTT typically occurs within the main electrical panel or at the point where the equipment grounding conductor enters the building, ensuring comprehensive protection against incoming surges. The benefits of implementing a GTT are multifold. Firstly, it provides robust protection for equipment against damage stemming from ground transients. Secondly, it enhances the reliability and uptime of equipment by preventing disruptions caused by transient events. Thirdly, it contributes to reduce maintenance costs by minimizing the need for repairs or replacements due to surge-related damage. Fourthly, and perhaps most importantly, it elevates the overall safety of the electrical system and the surrounding environment. The applications of the GTT span a diverse array of settings, including commercial buildings, industrial facilities, hospitals, data centers, telecommunication facilities, and even military installations, underscoring its versatility and widespread applicability. In conclusion, the GTT represents a cost-effective and efficient solution for shielding equipment from the adverse effects of ground transients. Its ease of installation and minimal maintenance requirements, coupled with its numerous benefits such as heightened equipment reliability, decreased maintenance expenditures, and fortified safety measures, position it as an invaluable asset for any organization seeking to safeguard its electrical infrastructure and assets. To further elaborate on the technical aspects, let's delve into the specific components and their roles within the GTT. Firstly, capacitors are crucial elements within the GTT design. Capacitors, in their most basic form, are electronic components capable of storing electrical energy in an electric field. They consist of two conductive plates separated by an insulating material known as a dielectric. The capacitance, measured in farads, quantifies the capacitor's ability to store charge for a given voltage. In the context of a GTT, capacitors serve to block the flow of direct current, or DC, while allowing alternating current, or AC, and transient surges to pass through. This characteristic is pivotal in diverting high-frequency transients to ground while maintaining the integrity of the grounding system for normal operating conditions. Secondly, inductors play a complementary role within the GTT circuitry. Inductors are passive components that store energy in a magnetic field when electrical current flows through them. They typically consist of a coil of wire, and their inductance, measured in henries, is determined by the coil's geometry, a number of turns, and the core material. Inductors exhibit the property of opposing changes in current flow. In other words, they resist sudden increases or decreases in current. Within the GTT, inductors serve to impede the rapid rise time of transient surges, thereby attenuating their peak voltage and reducing the stress on downstream equipment. By slowing down the rate of current change, inductors help to spread out the energy of the transient over a longer period, making it easier for the capacitors to divert it to ground. The combined effect of capacitors and inductors in the GTT creates a tuned circuit that is specifically designed to filter out high-frequency transients while allowing the fundamental frequency of the power system, typically 50 Hz or 60 Hz, to pass through unimpeded. This selective filtering ensures that the GTT does not interfere with the normal operation of the electrical system while providing effective protection against transient disturbances. In terms of installation considerations, the proper placement of the GTT is paramount for its optimal performance. As mentioned earlier, The GTT is typically installed in the main electrical panel or at the point of entry of the equipment grounding conductor into the building. This location ensures that the GTT intercepts transient surges before they can propagate throughout the electrical distribution system and reach sensitive equipment. It is essential to follow the manufacturer's instructions and adhere to relevant electrical codes and standards during the installation process. Proper grounding techniques are crucial to ensure that the diverted transient energy is safely dissipated into the earth. The equipment grounding conductor should be securely connected to a grounding electrode system that meets the requirements of the National Electrical Code, or NEC, or other applicable standards. The grounding electrode system typically consists of ground rods, ground plates, or connections to the building's metallic water pipe. The impedance of the grounding path should be kept as low as possible to minimize the voltage rise during a transient event. Regular inspection and maintenance of the GTT are also essential to ensure its continued effectiveness. The GTT should be visually inspected periodically for any signs of damage, such as cracked casings, loose connections, or corrosion. Electrical tests can be performed to verify the integrity of the capacitors and inductors and to ensure that they are functioning within their specified parameters. If any defects are detected, the GTT should be replaced or repaired promptly. Furthermore, it is important to consider the coordination of the GTT with other surge protection devices in the electrical system. Surge protective devices, or SPDs, are commonly installed at various points throughout the distribution system to provide layered protection against transient surges. The GTT should be coordinated with these SPD to ensure that they work together effectively to mitigate the impact of surges. Coordination involves selecting SPD with appropriate voltage protection levels and surge current ratings to ensure that they can handle the expected surge currents without failing. The GTT can be used in conjunction with SPD to provide a comprehensive surge protection strategy that protects equipment from a wide range of transient disturbances. Let's consider some specific examples of how the GTT can be applied in different types of facilities. In commercial buildings, the GTT can protect sensitive electronic equipment such as computers, servers, and telecommunications systems from damage caused by lightning strikes or power line faults. In industrial facilities, the GTT can safeguard critical process control equipment, motor drives, and programmable logic controllers, or PLCs, from transient surges that can disrupt production and cause costly downtime. In hospitals, the GTT can protect sensitive medical equipment such as MRI machines, CAT scanners, and patient monitoring systems from transient disturbances that can compromise patient safety and diagnostic accuracy. In data centers, the GTT can protect servers, storage devices, and network equipment from transient surges that can cause data loss, system crashes, and security breaches. In telecommunication facilities, the GTT can protect switching equipment, base stations, and transmission lines from transient surges that can disrupt communication services and damage infrastructure. In military installations, the GTT can protect radar systems, communication networks, and electronic warfare equipment from transient surges that can impair national security and defense capabilities. In addition to these specific applications, the GTT can also be used in residential settings to protect home electronics such as televisions, computers, and appliances from transient surges caused by lightning strikes or power line disturbances. While the cost of a GTT may seem significant upfront, it is important to consider the long-term cost savings that can be realized by preventing equipment damage, reducing downtime, and minimizing maintenance expenses. The GTT is a worthwhile investment for any organization or individual that values the reliability, safety, and longevity of their electrical equipment. To provide a more detailed understanding of the technical specifications of a GTT, let's examine some key parameters that are typically included in a product datasheet. Firstly, the voltage rating indicates the maximum voltage that the GTT can safely handle without experiencing insulation breakdown or other damage. The voltage rating should be selected to match the nominal voltage of the electrical system in which the GTT will be installed. Secondly, the surge current rating specifies the maximum surge current that the GTT can withstand without failing. The surge current rating is typically expressed in kiloamps, or kA, and they should be selected based on the expected surge currents in the electrical system. Factors to consider include the frequency and magnitude of lightning strikes, the proximity to power line faults, and the presence of other surge-generating equipment. Thirdly, the clamping voltage indicates the maximum voltage that the GTT will allow to pass through to the protected equipment during a surge event. The clamping voltage should be selected to be below the withstand voltage of the protected equipment to prevent damage. Fourthly, the response time indicates the speed at which the GTT reacts to a surge event. The response time is typically measured in nanoseconds, or ns, and it should be as fast as possible to effectively mitigate the impact of the surge. Fifthly, the operating frequency range specifies the range of frequencies over which the GTT is designed to operate effectively. The operating frequency range should be selected to match the frequency of the electrical system in which the GTT will be installed, typically 50 Hz or 60 Hz. Sixthly, the insertion loss indicates the amount of signal attenuation that the GTT introduces into the electrical system. The insertion loss should be as low as possible to minimize the impact on the performance of the protected equipment. Seventhly, the environmental rating specifies the environmental conditions under which the GTT is designed to operate. The environmental rating may include parameters such as temperature, humidity, altitude, and vibration. The GTT should be selected with an environmental rating that is appropriate for the intended application. Eighthly, the safety certifications indicate that the GTT has been tested and certified by an independent testing laboratory to meet applicable safety standards. Safety certifications provide assurance that the GTT has been designed and manufactured to meet rigorous safety requirements and that it is safe to use in the intended application. When selecting a GTT, it is important to consider all of these technical specifications and to choose a product that is appropriate for the specific application. It is also important to consult with a qualified electrical engineer or contractor to ensure that the GTT is properly installed and coordinated with other surge protection devices in the electrical system. In addition to the technical specifications, it is also important to consider the manufacturer of the GTT. Choose a reputable manufacturer with a proven track record of producing high-quality, reliable surge protection devices. Check the manufacturer's warranty and technical support services to ensure that you will receive adequate support if you encounter any problems with the GTT. By carefully considering all of these factors, you can select a GTT that will provide effective protection for your electrical equipment and ensure the safety and reliability of your electrical system. Let's now discuss some of the relevant standards and codes that govern the installation and application of surge protection devices, including GTT. The National Electrical Code, or NEC, is the primary electrical code in the United States. The NEC contains numerous provisions related to grounding, bonding, and surge protection. Article 250 of the NEC covers grounding and bonding requirements, including the requirements for equipment grounding conductors and grounding electrode systems. Article 280 of the NEC covers surge protection devices, including SPD and GTT. Article 280 specifies the requirements for the selection, installation, and coordination of surge protection devices. Other relevant standards include the Institute of Electrical and Electronics Engineers, or IEE, Standard 1100, which provides recommendations for powering and grounding electronic equipment in commercial buildings. IEE Standard C62.41 provides recommendations for surge testing and characterization of surge protection devices. Underwriters Laboratories, or UL, Standard 1449 is the safety standard for surge protective devices. UL 1449 specifies the requirements for the design, construction, and testing of SPD and GTT. These standards and codes provide guidance for the safe and effective installation and application of surge protection devices. It is important to be familiar with these standards and codes and to follow them carefully when installing and using GTT. Failure to comply with these standards and codes can result in unsafe conditions and equipment damage. In conclusion, the Ground Transient Terminator is a valuable tool for protecting electrical equipment from the damaging effects of ground transients. By diverting transient energy to ground, the GTT can prevent equipment damage, reduce downtime, minimize maintenance expenses, and improve safety. The GTT is suitable for use in a wide variety of applications, including commercial buildings, industrial facilities, hospitals, data centers, telecommunication facilities, military installations, and residential settings. When selecting a GTT, it is important to consider the technical specifications, the manufacturer's reputation, and the relevant standards and codes. By carefully considering all of these factors, you can select a GTT that will provide effective protection for your electrical equipment and ensure the safety and reliability of your electrical system. Remember to consult with a qualified electrical engineer or contractor to ensure that the GTT is properly installed and coordinated with other surge protection devices in the electrical system. Proper grounding techniques are crucial to ensure that the diverted transient energy is safely dissipated into the earth. Regular inspection and maintenance of the GTT are also essential to ensure its continued effectiveness. By following these guidelines, you can maximize the benefits of the GTT and protect your electrical equipment from the damaging effects of ground transients. Understanding transient voltage surge suppressors, or TVSS, and their relationship to GTT can provide further clarity. While the terms are sometimes used interchangeably, TVSS is a broader term encompassing various devices designed to protect against voltage surges and spikes. A GTT specifically addressing ground transients can be considered a specialized type of TVSS. TVSS devices, in general, work by detecting overvoltage conditions and diverting the excess energy away from sensitive equipment. This diversion is typically achieved through components like metal oxide varistors, or MOVs, silicon avalanche diodes, or SADs, and gas discharge tubes, or GTTs. MOV are commonly used in TVSS devices due to their ability to handle high surge currents and their relatively low cost. They function by changing their resistance in response to voltage variations, shunting excess current to ground when the voltage exceeds a certain threshold. SAD are another type of semiconductor device used for surge suppression. They offer faster response times compared to MOV but typically have lower surge current handling capabilities. GDT are gas-filled tubes that provide a high impedance path under normal conditions. However, when a voltage surge occurs, the gas ionizes, creating a low impedance path that diverts the surge current to ground. The choice of components and the design of the TVSS device depend on the specific application and the level of protection required. Factors to consider include the expected surge current levels, the sensitivity of the protected equipment, and the environmental conditions. In addition to the components mentioned above, TVSS devices may also include filters to attenuate high-frequency noise and indicators to signal the status of the surge protection. Filters can help to reduce electromagnetic interference, or EMI, and radio frequency interference, or RFI, which can also disrupt the operation of electronic equipment. Indicators, such as LED, can provide a visual indication of whether the TVSS device is functioning properly and whether it has absorbed any surges. TVSS devices are available in a variety of form factors, including plug-in strips, hardwired panels, and rack-mounted units. Plug-in strips are commonly used in residential and office environments to protect individual electronic devices. Hardwired panels are typically installed at the service entrance of a building to provide whole-house surge protection. Rack-mounted units are designed for use in data centers and other critical facilities where high levels of surge protection are required. When selecting a TVSS device, it is important to consider the let-through voltage, which is the maximum voltage that the device will allow to pass through to the protected equipment during a surge event. The let-through voltage should be below the withstand voltage of the protected equipment to prevent damage. It is also important to consider the surge current capacity, which is the maximum surge current the device can withstand without failing. The surge current capacity should be selected based on the expected surge currents in the electrical system. Furthermore, consider the clamping voltage. A lower clamping voltage offers better protection. And of course, the energy absorption capacity, measured in joules, indicates how much energy the TVSS can absorb before it needs replacement. TVSS devices are an essential component of any comprehensive electrical protection strategy. By diverting voltage surges and spikes away from sensitive equipment, they can prevent equipment damage, reduce downtime, and minimize maintenance expenses. When selecting a TVSS device, it is important to consider the specific application, the level of protection required, and the relevant standards and codes. Remember to consult with a qualified electrical engineer or contractor to ensure that the TVSS device is properly installed and coordinated with other protective devices in the electrical system.